But the next revolution in spacesuit technology goes far beyond mechanical improvements to create something that would have seemed like science fiction just a few years ago. Smart fabrics and AI integration. Spacesuits now incorporate smart fabrics that transform protective equipment into intelligent monitoring systems. These advanced textiles continuously track astronaut health and suit performance through sensors woven directly into the fabric itself. The integration represents a fundamental shift from passive protection to active health and safety management that provides real-time data to both crew members and mission control. Smart fabrics embedded throughout modern suits monitor astronaut health parameters with medical-grade precision. Sensors woven directly into the fabric track heart rate, blood pressure, respiratory rate, and body temperature without requiring separate monitoring equipment that could fail or interfere with suit operations. The fabric can detect changes in skin conductivity that indicate stress levels, dehydration, or fatigue before astronauts consciously recognize these conditions themselves. Temperature sensors distributed throughout the suit fabric create thermal maps that reveal hot spots or cold zones that could indicate circulation problems or equipment malfunctions. These health monitoring systems provide early warning of medical emergencies that could incapacitate astronauts during critical operations. The smart fabrics can detect irregular heartbeats, dangerous blood pressure spikes, or signs of heat exhaustion before these conditions become life-threatening. Advanced algorithms analyze patterns in vital signs to predict when astronauts might need rest breaks or medical intervention. The continuous monitoring enables mission control to track crew health status in real time and make informed decisions about mission duration and task assignments. NASA's collaboration with Corsients has enhanced carbon dioxide monitoring inside next-generation spacesuits using advanced capnography modules embedded directly into smart fabric systems. These sensors provide continuous CO2 level monitoring while reducing helmet noise and airflow requirements, making the suits safer and more energy efficient. The embedded capnography represents a significant advancement over traditional monitoring systems by integrating seamlessly with the suit's fabric structure rather than requiring separate equipment that adds weight and complexity. Suit integrity monitoring through smart fabrics represents a breakthrough in detecting structural problems before they become catastrophic failures. Microscopic sensors embedded in the suit's pressure-bearing layers can detect stress fractures, seal degradation, or material fatigue that could lead to dangerous pressure losses. The fabric sensors monitor pressure distribution throughout the suit, identifying areas experiencing abnormal stress that might indicate impending failures. These systems can detect micrometeorite impacts or punctures that create tiny holes, alerting astronauts to problems while they still have time to implement emergency procedures. Structural health monitoring sensors integrated into glove systems provide critical feedback about the most vulnerable components of spacesuits. Gloves experience the highest stress and wear during spacewalks because astronauts use their hands for virtually every task. Smart sensors embedded in glove materials track stress patterns, detect developing tears or punctures, and monitor joint where that could compromise pressure integrity. These monitoring systems alert astronauts to glove problems before they become dangerous, enabling preventive action or emergency procedures to maintain safety during critical operations. Environmental condition monitoring through fabric sensors provides detailed information about external conditions that affect suit performance and astronaut safety. Temperature sensors throughout the outer fabric layers track thermal loads from solar radiation and identify dangerous temperature gradients that could damage suit components. Radiation detectors woven into the fabric monitor cosmic ray exposure and solar particle events that pose health risks during extended missions. Humidity sensors track moisture levels that could affect suit performance or create uncomfortable conditions during long spacewalks. Machine learning algorithms integrated into NASA's primary life support system control loops analyze sensor data to optimize suit performance automatically. These systems process thousands of data points per second, identifying patterns that indicate developing problems with life support systems, mobility components, or structural integrity. The algorithms learn from operational data collected during actual missions, continuously improving their ability to predict and prevent failures. The machine learning can recognize subtle changes in system performance that human operators might miss, providing early warnings that enable preventive action. Real-time feedback systems provide both astronauts and mission control with instant access to comprehensive suit status information. Smart fabric sensors feed data to processing systems that generate immediate alerts about any conditions requiring attention. The systems can distinguish between minor variations in normal operation and significant problems that require immediate response. Mission control receives the same real-time data that astronauts see, enabling coordinated responses to emergencies and informed decision-making about mission continuation or abort procedures. Data collection systems built into smart fabrics gather information that advances spacesuit technology for future missions. Every spacewalk generates thousands of data points about suit performance, environmental conditions, and astronaut physiology that inform design improvements. The comprehensive data collection enables engineers to identify design weaknesses, validate performance models, and develop better solutions for future suit generations. This continuous feedback loop between operational experience and design improvement accelerates the pace of technological advancement. Smart systems reduce mental workload during complex tasks by handling routine monitoring and management functions automatically. Astronauts can focus entirely on scientific experiments, construction activities, or emergency procedures without constantly checking suit status or making manual adjustments. The systems provide relevant information when needed while filtering out routine data that would otherwise create distractions. This reduction in cognitive load improves astronaut performance and reduces the risk of errors caused by divided attention during critical operations. These intelligent monitoring capabilities represent just one aspect of how modern suits have evolved beyond simple protection into sophisticated systems that enhance every aspect of astronaut operations, including the fundamental ability to stay connected with their teams and mission control throughout the most challenging environments humans have ever encountered. Communication, revolution, staying connected. Modern space suits function as sophisticated communication command centers that manage voice, data, video, and telemetry simultaneously across multiple channels and frequencies. These integrated networks coordinate communications between individual astronauts, spacecraft systems, ground control, and backup networks without requiring astronauts to manually switch between different devices or manage complex routing decisions. This transformation from simple radio systems to comprehensive communication hubs represents one of the most dramatic advances in spacesuit technology. Integrated communication systems eliminate the traditional Snoopy cap headgear that astronauts wore for decades inside their helmets. The XMU suits designed for the Artemis program feature a new audio system built directly into the helmet structure, ensuring consistent audio quality regardless of head position or movement during complex tasks. Previous suits required separate headsets with foam earpieces and microphone booms that could shift during movement, creating dead zones where astronauts couldn't hear or be heard clearly. The integrated communication system includes speakers mounted inside the helmet and several embedded voice-activated microphones that automatically pick up when an astronaut is talking to mission control or crewmates. These voice-activated systems distinguish between intentional communication and background noise, breathing sounds, or casual conversation that shouldn't be transmitted. The microphones use advanced noise cancellation technology that filters out the constant hum of life support systems, fan noise, and other mechanical sounds that would otherwise interfere with clear communication. Multiple microphones provide redundancy and enable the system to maintain clear audio even if individual components fail. Advanced audio systems provide crystal clear communication despite the challenging acoustic environment inside pressurized suits. Space suits create noisy environments filled with the constant sounds of fans, pumps, motors, and airflow that can overwhelm traditional communication systems. Modern audio processing uses digital signal processing algorithms that automatically adjust volume levels, filter background noise, and enhance speech clarity in real time. The systems can distinguish between different types of sounds and prioritize human voice frequencies while suppressing mechanical noise that would make communication difficult. The helmet design provides improved acoustic isolation that enhances communication quality while reducing fatigue from constant noise exposure. Better sealing around the neck and improved internal padding reduce external noise intrusion while creating more controlled acoustic environments inside the helmet. The audio systems use directional speakers that focus sound toward the astronaut's ears rather than filling the entire helmet volume with audio. This targeted approach reduces overall noise levels while improving speech intelligibility during extended missions. Modern suits integrate simultaneously with multiple communication networks that operate on different frequencies and protocols. Astronauts can maintain contact with their immediate crew members through short-range radio links while simultaneously communicating with spacecraft systems and ground control through separate channels. The suits automatically manage these multiple connections, routing communications to appropriate destinations based on content and priority levels. Emergency communications receive automatic priority routing that overrides routine traffic and ensures critical messages reach their destinations immediately. The communication systems work seamlessly across different spacecraft designs and space agencies that use incompatible radio protocols and frequencies. International Space Station operations require suits that can communicate with Russian, American, European, and Japanese systems simultaneously. The suits include software-defined radios that can be reconfigured to work with different communication standards without requiring hardware changes. This flexibility enables crew members from different countries to work together effectively while maintaining contact with their respective ground control centers. Heads-up displays integrated into helmet visors provide visual communication capabilities that supplement traditional audio systems. These transparent displays show text messages, system status information, and navigation data directly in the astronaut's field of view without requiring them to look away from their work. The displays can show communications from multiple sources simultaneously, using different colors and positioning to distinguish between routine updates and urgent messages. Augmented reality features overlaid digital information onto the real world, providing context-sensitive data about objects and equipment in the astronaut's environment. Backup communication systems ensure astronauts never become completely isolated from safety networks, even when primary systems experience failures. Secondary radio systems operate on different frequencies and power sources, providing redundant pathways for emergency communications. The suits include emergency beacon systems that automatically activate if life support or communication systems detect dangerous conditions. These backup systems can operate independently of main suit power, using dedicated batteries that provide several hours of emergency communication capability. Emergency communication protocols automatically route distress signals to multiple destinations simultaneously, ensuring that help requests reach ground control, nearby crew members, and spacecraft systems even if individual communication paths fail. The backup systems include automated distress messaging that transmits astronaut identification, location data, and basic telemetry even if the crew member becomes incapacitated. The increased activity in space operations drives the need for these advanced communication systems. NASA's current astronaut corps includes 46 active astronauts representing unprecedented diversity in backgrounds and expertise, with commercial crew programs bringing additional complexity to communication requirements. The year 2025 saw over 200 EVA hours, double the 2018 figure, reflecting the growing scope and complexity of space operations. Since the International Space Station's assembly began, astronauts have completed 248 EVAs, each requiring flawless communication systems to ensure mission success and crew safety. Better communication directly improves safety and mission success by enabling faster response to emergencies and more effective coordination during complex operations. Clear, reliable communication allows ground control to provide real-time guidance during challenging tasks and enables crew members to coordinate their activities more effectively. Enhanced communication also reduces the psychological stress of isolation that can affect astronaut performance during long missions far from Earth. Next-generation communication features will transform how astronauts work by enabling real-time collaboration with experts on Earth and other crew members across vast distances. Upcoming systems will support high-definition video streaming, three-dimensional mapping data, and interactive augmented reality that connects astronauts with remote technical support teams. These advanced capabilities will enable complex operations that require expertise not available among the immediate crew members. However, even the most sophisticated communication systems and life support technologies cannot address every challenge that astronauts face during extended operations in space.